here first. And the first thing that you guys need to know is that there isn't just one parent function. So this differs from all the other functions we've studied. And all the other functions that we've studied, you memorize one parent function and that's it. The parent function for an exponential function is always going to have a base, and then it's going to be raised to a power of x. The tricky part is that base can be anything that creates an exponential growth or decay function. So it's going to be a positive value. It won't be 0, it won't be 1, but it can be any different number. So this is a parent function right here, but it's not the exponential parent function. It is one example of an exponential parent function. Is that okay with everybody? Does that make sense? All right. And in this exponential parent function, the base is 2. Okay. Since we can use any type of exponent, for our parent functions, we will still use the numbers surrounding 0, like we're most familiar with for most of our parent functions. So we can use those because we can plug in any type of exponent, negative, positives, fractions. So we stick with wanting to see what's happening at 0 and around it, okay? You can't memorize one parent function. You can memorize this, but then based on the base, okay? Depending on what this actual parent function is, will determine the values for y, okay? So our y values in this case will be when 2 is raised to the powers. So when 2 is raised to the second power, the result would be 4. When 2 is raised to the first power, the result would be 2. When 2 is raised to the 0 power, it will be 1. When 2 is raised to the negative 1 power, it will be 1/2, and 2 to the negative 2 power will be 1/4. And what kind of answers can I not get for this function? No matter, I'm allowed to plug anything in. So the domain is all real numbers, right? I can plug in anything for x. What will I never get as an answer if what I'm doing is taking 2 and raising it to the number that you give me? So you can give me all kind of numbers. I try to do the calculation. What kind of answer will I never achieve? Cool. A negative, okay, and what else? And 0. So what happens is you can get smaller and smaller and smaller, like you see right here, 1/2, 1/4. We can get smaller and smaller, but we'll never actually reach 0, even though we're getting closer and closer and closer to it. So all of our parent functions have this barrier at 0, which is going to be that asymptote that we talked about. It's a horizontal asymptote because it's setting a boundary for the outcomes, the y values. The y values here will never be 0, and they will never be negative in a parent function. So this asymptote is that horizontal line, and it has the equation y equals 0. And honestly, I personally like to kind of include it in my parent function, because then when I transform the table, I could also just transform the asymptote if I wanted to. Okay, and then I'm going to plot the rest of these points. So negative 2, 1/4. Negative 1, 1/2, 0, 1, 1, 2, and 2, 4. And then you see a curve like you guys saw in the investigation. And you see that one end of the curve has end behavior that's going towards either infinity or negative infinity. And the other end of the curve has end behavior that kind of goes towards one specific number, but never actually reaches that value. Okay? Is everybody okay with the shape of the graph and why we have like that horizontal asymptote as a characteristic of the parent function? All right, so let's go ahead and remind ourselves about these. Now, I wrote the h and k a little bit differently on purpose. I didn't put them into a point because here's why. What is h in our parent function? The parent function has no shifting. So what is h in our parent function? 0, and k is 0. Does this function actually have the point 0, 0? No, okay? 0, 0 is here. It might kind of be like what our graph is centered around, but it's not an actual point on the graph anymore. So this is a little bit different too. H and K don't necessarily make a point for us. We saw this with our reciprocal function as well. So that's why we're just identifying H and K and not writing it as a point, okay? The X intercepts here would be none, okay, because it's not reaching that X-axis, that asymptote. the y-intercept would be 0, 1. And every parent exponential function will have the same y-intercept. Is that okay with everybody? So look back at that equation. Think about parent functions. They're just a base raised to a power. So anything to the 0 power always ends up being 1. So all the parent functions have this 0, 1 point. Okay? What's our domain? All real numbers. Okay, you can plug in any exponent. So all reals or negative infinity to infinity, and you can see on the graph that you could go as far left or right as you want, and the graph still exists. What about our range? Y is greater than 0, right? It has a boundary at 0, but a boundary that we don't reach. So either we write it as y is greater than 0, or an interval notation from 0 to infinity. Notice that they both have the parenthesis type of brackets because we don't actually reach 0. Okay. All right. Is this graph increasing or decreasing? Increasing the entire domain. The entire domain is all real numbers. So the increasing interval is the interval from negative infinity to infinity, and there is no decreasing interval. Is this function 1 to 1? Does it pass? Is it a function, first of all? Yeah, it passed the vertical line test. Does it pass the horizontal line test, the inverse of that? Yes. So is it 1 to 1? Yes. And now, based on our last unit, what does that tell you guys about this function? Its inverse is also a function, right? Okay. What kind of function? We'll find out later in this unit, right? The rate of change and this axis of symmetry here are not applicable to this type of function. Rate of change, technically, you guys, your pre-calc teacher and stuff would say, we say varies, and you'll explore how the function is changing later on, okay, in the pre-calc honors towards the second half of it. Okay, minimum value and maximum value. Is there one specific y value that you can identify this is the highest the function will reach? No. Is there one specific value that you can identify that says this is the lowest the function can reach? No, it's weird. We have a boundary, but we don't have a minimum value. There is not a y value that I can say, here is the lowest y value the graph hits. It technically keeps getting lower and lower, even though it does have a boundary. And we can't say 0 because we don't actually reach 0. Okay? And if I ask you, what's the number right before 0 that you reach? Well, there's infinitely many of them, and so we can't pick that out. All right? So there is actually no minimum and no maximum. And what kind of asymptote are we seeing in this function? Y equals 0, which is a horizontal asymptote. So we'll put that there, and there isn't any vertical type of boundary. Okay? Now, the rest of the equations on this handout deal with a base of 2 so that you can use the parent function that we built. But do you guys understand that if we looked at the next problem, and if instead of having a 2 right here, it had a 3 or a 4 or a 1/2 or a 1/4 or a 1/3, we would have to build a new parent function different from using 2 before we could do the transformed function. Does that make sense to everybody? All right. So the ones on this paper are examples of transformations of the specific parent function we started with, but you'd have to start with a different parent function if they are different. Okay. We're going to do the Algebra 2 Trig 1 together. So flip it over. There is one on the back side. All right, when you guys look at this function, some things that's important for you to notice. First of all, the negative is not part of the base. It wasn't included in parentheses. Actually, you're not going to study any exponential functions with a negative base. They're actually defined not to have a negative base because they would not make that smooth curve. Because what happens when you raise a negative number to different powers? If you raise a negative number to even powers, what kind of result do you get? Positive. But if I raise a negative number to odd powers, what kind of result do I get? Negative. So that graph would go like, would start bouncing back and forth between the positives and negatives, getting closer together or further apart. It's a whole different type of graph. So when we say exponential functions, we're putting a limitation on the base as only being a positive type of value, okay? So number one, we're not studying that. Number two, even if I didn't tell you that, do you guys understand the way this function is written? That negative is not part of the base. They didn't group it with the 2 and then put the power on it, which means the power is only applying to the 2, okay? Second thing is, this exponent is not written in the form that we want. We need to separate our b value from our x minus h value. Just like we've done with every other function, now the inside of the function is what's stuck up in the exponent. Okay? Because this is a base of 2, you guys do have our parent function that we already did. So I'm just writing down the parent function from the other side, and we talked about how we would figure that out. And then let's talk about what our transformation table is going to look like. So I want one person to tell me in words a kind of transformation we have, and then I want another person to tell me how that means I'm going to write it into this table to calculate what's happening on the graph. So somebody identify one piece from the equation and tell me in words what kind of transformation that's causing of the parent function. Okay, do this. Take 1 minute in your group, look at all the numbers in the equation and decide with each other all the transformations, and then I'm going to ask you guys again, okay? Go. Okay, she says a shift up 4. Do you guys see where that's happening? Okay, so she's looking at this. She's saying verbally what that means is we have a shift up 4. Somebody tell me how that's going to look when I'm trying to adjust my points. How do I put this as the headers on my table? How do I adjust my points to move up 4? Stefan? Okay, so in this column where we're controlling the y distances, we're going to eventually want to add a 4 to them. All right, somebody else, give me a different transformation that we see up here. Andrew. Okay, so he says a shift right 2. Does everybody see where he's picking that out? So right here, h is actually a positive 2, and that's giving us the shift right 2. Somebody different, tell me how I'm going to make sure to incorporate that as I'm calculating the distances of these points. What is that going to look like in my table? Zoe. Good. So in the x column, I'm going to make sure that I eventually add 2 after I'm done with everything else to move everything to the right 2. Okay. Somebody else, give me a different transformation that we see up here. Susan? Okay, good. And what axis are we reflecting over? So the reflection's out here, right? The negative is out here. Is it going to affect x or y values? It's going to affect y values, right? Because it's not affecting x, okay? So what we're going to see is it happening here. If you change the sign of a y value in a point, which axis do you reflect that point over? The x-axis. Okay. All right, what else? Somebody else give me another transformation that's on here. So we've addressed the 4, the 2, this negative. What haven't we addressed? Jake? Good, except for it's actually a horizontal compression. Good. And that's exactly why. Because though it's a 3 in the equation, right, we've studied that that 3 is a 3 inside the equation. When you plug something in for x, it takes it, it times it by 3. But the effect that has on the distances on the graph is actually to make them a third of what they were before, which is why it's a horizontal compression. Okay? Do we do anything with this 2 in our transformations? No, this 2 is not a transformation. That 2 is part of the parent function. Does everybody understand that? Okay, so if you used it to make the parent function, which is how the base should be used to make the parent function, it shouldn't be performing any transformations because you already used its value to make your initial chart. Okay? All right, so now if we go through these, if I take, I'm just starting right here, if I take negative 2 times it by a third and then add 2, so that's negative 2/3 plus 2, so that would be 1 1/3. And then if I multiply by negative 1 by a third, that's negative 1/3 plus 2 would be 1 2/3. 0 will give me 2. With 1, I'll get 2 1/3. 2, I'll get 2 2/3. Okay. If you take longer to do the fraction math, that's fine. Take the time that you need. But We're just going through this for demonstration purposes. If I had a negative 1/4 plus 4, that would be 3 3/4. Negative 1/2 plus 4 would be 3 1/2. Okay. Negative 1 plus 4, negative 2 plus 4, negative 4 plus 4. Okay. And then the other thing we want to keep track of is our asymptote. In our parent functions, our asymptote is at 0. What is the only transformation that's going to move that asymptote? So I'm going to go back to my previous graph so you guys can visually see it. If I have a graph like this, okay, if I horizontally stretch or compress it, is that going to change the location of the asymptote? No. Okay. If I vertically stretch or compress it, is it going to change the location of the asymptote? No, because my distances are getting further and closer to 0, but the asymptote was on 0, so like that's not going to work. If I reflect, does it change the asymptote over the axes? No. Okay. If I shift left and right, does it change the asymptote? No. What's the only transformation that changes this asymptote? Shifting up or down. Do you guys see that? Okay. So when we go back here, that means you have a couple of ways to determine your asymptote. If you know that, which number from the equation caused a shift up or down? 4. There was a shift up 4. So instead of my asymptote being at 0, my asymptote's going to be at positive 4. Also, you could literally do the same thing you've done to every other y value. This was a y value of 0. All of the y values got taken their opposite and add 4. And if you do that with 0, you also get 4. So you could look at it as a transformation. You can understand that only the vertical shift changes the asymptote and have that value. And so now I'm going to go ahead and I'm going to plot these points. I'm going to zoom out for a minute so that I can make sure I plot it correctly. So I'm going to put this asymptote at 4. And then it says 1 1/3, 3 3/4. A little annoying to plot, but somewhere up there. 1 2/3, 3 1/2. Oh, I'm not going 1, sorry. Shoot. Two, 3, 2 1/3, 2, 2 2/3, 0. All right. So thirds and 2/3 make our points kind of all squished together, but that's because we had that horizontal compression. Does the shape look right? Are all the points on one side of the asymptote? That should occur. And do you see the place where it's going away from the asymptote versus where it's going towards the asymptote? And that's how we want to fill in our curve. So I can fill in the part that's going away from the asymptote here and then towards the asymptote here if I'm struggling a little bit with drawing that curve. Probably not as flat as I drew it, but I can't get across the point, so that'll do. Okay. Is this idea okay with everybody? Okay. So what I just tried to do with you guys is go back through transformations, and either you're tired or you need to review what they are so that you transform things correctly with the points. Okay. And so I wanted to go back through that. We did it in words and we did the chart. There's no difference in transformations than there was before. Probably the biggest difference here in the parent function is that there could be lots of different parent functions. You need to identify the base, and that one of the numbers in your equation is part of the parent function. You have to make sure you lock that in so you're not trying to use it as a transformation. Okay, so I'm going to give you guys some time with the people in your groups. Go through and fill in the characteristics of this function. Okay. See what you can and can't figure out in that chart, and then we'll come back to it in a few minutes. And then if you guys are ahead of us, go and do the other graph that was on the other side. Okay, it's a little bit simpler. It's just more regular algebra 2 style. It has no horizontal stretching or compressing. Okay. And let's just check the characteristics, and I'll talk specifically about X and Y intercepts in a minute. So our H and K values were 2 and 4. We're just literally picking out the H and the K from the equation. All right. I'll come back to X and Y intervals, or X and Y intercepts. So domain and range. Are we okay with the domain being all reals and that the range is y is less than 4? Be careful with your intervals. Some of you guys on your final and on the last test, you need to always write your interval with the smaller value, comma, the larger value. Okay. And then this one, given the direction that it went, is decreasing the entire time. So no increasing interval, but decreasing interval over the entire domain. All of these are going to be 1 to 1. Okay. And then we should have a horizontal asymptote at 4. Any questions about those things before I address the intercepts? Okay, so technically finding intercepts is not new, but what makes intercepts difficult is that you're always solving an equation, but we're solving several different kinds of equations, and they all have slightly different things that we look at when we try to solve them. So I'm going to look at the y-intercept first, because our equations are written in a way where finding the y-intercept means you're just plugging in and following order of operations. So this is me finding the y-intercept. Okay. So I took the equation, I plugged in 0 for x. So the first thing I did was calculate what value is in the exponent here. 3 times 0 minus 6 gives me a negative 6 in the exponent. Okay. Remember, this negative is not part of what's being raised to the power. So 2 to the negative 6 means 1 over 2 to the 6th, which would be 1 over 64. So I have a negative 1 over 64 being added with 4. The way I do this is like I have decent number sense. I just think about having 4 positives and trying to take away this very small piece means I'm going to have 3 positives and almost the rest of the last 4. Since it was broken into 64 parts and I'm taking away one of them, that means I have 3 left with 63 out of the 64 parts. And that's a number very, very, very close to 4, which is very, very, very close to our asymptote, and that should kind of match up with what your graph looks like. Okay. So the y-intercept is always going to be a calculation. I'm not saying it's easy, okay, but you shouldn't have to move anything around or solve for anything. You should just have to finish the calculation. Up here is the x-intercept. So to find an x-intercept, we set y equal to 0, and then we try to isolate x. So when x is stuck in the exponent, the first thing to do is to focus on isolating the power that contains the exponent, okay? So I subtracted 4, then I divided by negative 1, because remember that negative is not part of that power. So then I had 2 to this power equals 4. We don't really have a way to solve that, except for here we do know 4 as a power of 2. 4 is really the same thing as 2 to the second power. So the only way that 2 to this power is going to equal 4 is if the power here ends up equaling 2. So when I write these like this, when I know that 4 is 2 to the second and this is 2 to this, that would be like me asking you guys, what power would you put on 2 to get 2 to the 4th power? Not a trick question. What power would you put on 2 so that it equals 2 to the 4th power? 4, okay? And there's no special like solving. You didn't cancel out 2's. Like I didn't cancel these out. I just know that if I want these 2 exponent powers to be equal and they have the same base, their exponents have to be equal too. So basically the 3x minus 6 has to equal 2 or there's no way this is going to work. Is that okay with everybody? So I set that equal here and I got 8/3. We're going to have a lot more practice with that. It should have felt a little mysterious right now. If you got it, you should feel like a very true problem solver because it was kind of a tough little problem. Okay? Any questions about this one? All right, let's look on the front side. So here's the points I got for my graph. So here's my table of points. I took my x values and shifted them to the left 3, okay, because my h was -3. I took my y values, I shifted them down 1 because my k was -1, okay? And then, so here's my asymptote at y equals -1 instead of at 0. And then here's the points. Notice it looks almost exactly like your parent function. You guys have them side by side. Compare them. The spread of points is literally exactly the same because this graph didn't have any stretches or compressions. It just took the points and moved them all over to the left 3 and down 1. And so this is basically a snapshot of that graph, literally moved to the left 3 and down 1 since there weren't any stretches and compressions. Is that okay with everybody as far as the points go? All right. So your h was -3. Yeah. Like that there. And your k was -1. I'll come back. Well, no, we'll do the intercepts because we already talked about them. So again, here's my x-intercept. I set y equal to 0. And then I go to solve. Remember, solve means get the piece that contains x alone first and then figure out what you have to do to figure that out. So I added 1 to the other side first. And then just like last time, I had sitting here 2 to some power equals 1. So I thought in my head, like, do I know a power of 2 that makes 1? And I actually do. 1 would be the same thing as having 2 raised to the power of 0. Okay, so here I basically know that for these two things to be equal, the x plus 3 exponent would have to come out to be 0, otherwise it won't equal the 1 that's there. Okay, so I set those equal and finished solving and got x equals -3. Okay, for my y-intercept, it's right here. You see that I plugged 0 in for x, and then I just have to finish this calculation. So first, the exponent is a 3. 2 to the third is 8. 8 minus 1 leaves me with 7. Okay, are we okay with the intercepts here? All right, and then domain, all real numbers are -infinity to infinity. Our range is that y is greater than -1 or -1 to infinity. The entire graph was increasing, so the entire domain is listed as the increasing interval with no decreasing interval. It is 1 to 1, okay? Rate of change and axis of symmetry are not something we're studying about this function. No minimum or maximum value, and then we end up with that horizontal asymptote at -1 and no vertical asymptote, okay? Any questions that you guys have?